Hi everyone, welcome to Best Science Brain YouTube channel. Today we're taking a look at Physics Practicals Alternative B, WAEC 2024 May-June examination. Question number 1. This is the model 2 or question number 1. We have done the model 1. As I said, this question number 1 involved the use of ray bursts, the converging lens, and a wide screen. So in the first model, if you stream our videos, you're going to see the first model was released some hours ago, or a few hours ago. So in the first model, we tried to explain that we presented the equipment required, we presented the converging lens, we also showed you guys the screen and the ray bursts, if you have not seen them before. So the same spacemen that we are still dealing with in this question. I will say in the first video that questions can be asked in different manner or in different form from the same equipment. The only difference is what you are measuring. So present this model 2, and in this model 2 you're going to see that the parameters we're going to measure is different from the one we measured in model 1 of the same question 1 specimen. So as we said, as I promised, we're going to bring 3 models for this question 1 to show or to showcase different ways by which you can bring question from that involve this optics, that is a converging lens, ray burst, and then the screen. So at this point in time, we are not doing the live experiment. Rather, we're showing you how to obtain your values by calculations to obtain perfect values that can also be evaluated as experimental values. So we have the ray burst there. You can see the bulb inside of it, illuminating the ray burst. On the ray burst, you see the cross wire there and the opening. That is the hole on the ray burst. And the AO there stands for the diameter of the ray burst, and that is the hole there, and that is the object height or object size, because that cross wire there is your object. Then the distance between the ray burst and the lens is labeled L, is called the object distance, while the distance between the lens and the screen is called the image distance. So here U stand for the object distance and V stand for image distance, whereas S stand for the screen. For the fact that we use U and V in this diagram, you shouldn't expect that WAEC will use U and V as well. You can see change it to S and Y. Just like when we described the experiment, when we did the experiment on relative density up trough for those that took alternative A. And after the experiment, we also brought a video to show how you can manipulate your readings by calculation. I told you guys that in my video I used W1 as the weight of the object in air, W2 as the apparent weight in water, W3 as the apparent weight in kerosene. I also told you that way you can change those letters. You look at the exam they took in alternative A, then I use WA in place of W1 for the weight in air, and then they use WB for WW for the weight in water, and so on. So the important thing is to know what you are looking for and then know how to go about it. So let's go to the question once more again before we now go to the calculations. You are provided with illuminated object, converging lens, screen, meter rule, and other necessary materials. I measure and record the size AO of the illuminated object. That the size AO, you can see there, the diameter of the hole on the ray burst. I play the object O and the screen S on opposite size of the converging lens. L. The object is your ray bus. That is, your ray bus is the object, while the screen is on the other side. So the lens will be in between the object and the ray bus and the screen. Sorry. Then number 3 says, set the distance between the object and the lens as that u equal 30 cm. That the distance between the ray bus and the lens u is 30 cm. Then IV, adjust the screen until a sharp image of the related object is obtained on the screen. So we're going to adjust the screen. In the ray experiment, you shift the screen forward and backward until a sharp image of this cross wire is formed on the screen. So number 5, V. Measured and record V, the distance between the lens and the screen S. So when the sharp image is formed on the screen, you now measure and record the distance between the lens and the screen, and that is your V, which is our image distance. So provided is V they use, they can use Y for V and they can use S for U. They can use different letters. So you should understand the concept. Then VI says evaluate U inverse and V inverse. VII says repeat the experiment for 4 other values of U, 45 cm, 40 cm, 45 cm, and 50 cm, respectively. And then VII, tabulate your readings. Then IS, plot a graph of V inverse on the vertical axis or on the ordinate against U inverse on the horizontal axis. So we'll look at the question once more. Then question S say determine the slope S of the graph and the intercepts C1 and C2 on both axes. Then SI say evaluate C equal to C1 plus C2 over 2, that the average or the mean of the intercepts. Hence, determine K equal to 1 over C. Then SII, state the precautions taken to ensure accurate results. So let's go to the questions, or let's go to the calculations now. So this is the table of reading prepared for our experiment. And then AO, as we said, is the size of the opening on the ray, the diameter of the crosswire on the ray bus. So, and we are taking 2.500 as the size of that opening on the ray bus, that the diameter of the crosswire. So you use a ruler to measure it. So you can, as I explained in the first video, you can take 1.5, you can take 2.0, you can take 2.5, you can take 3.0, you can take 3.5, you can take 4.0. So from 1.5 to 4.0, any value you take is okay. So provided you are consistent in the value you're using in calculation. So this stands for the size of the object, because the ray bus, that is the opening on the ray or the crosswire that should be there, stand for our object. So that the object size or object height. Now for number 1 experiment, we are told to set the object at a distance of 30 cm, 30 centimeter from, that is the lens, at a distance of 30 cm from the ray bus. So that becomes our U or object distance. So record here our U as 30.00 cm. So record as number 1, 30.00 centimeter. That is our object distance. So we're going to evaluate our V, then evaluate our U inverse and V inverse. So we'll go to the calculation now. To evaluate our V, we bring in the length formula, making 1 over V the subject. 1 over V is equal to 1 over F minus 1 over U. Then we'll take the LCM of on the right hand side, F and U, that is U over F. So divide U F by F, you have U, so U goes up. Divide U F by U, you have F, so F goes up. So you now have U minus F all over U F equal to 1 over V. So invert both sides. V over 1 gives you U F all over U minus F. So V over 1 on this side, then invert this side, have U F all over U minus F. So that formula is very important for the calculation. So which you're going to use to derive the object distances of all the image distances of all the objects at the different locations. Now we'll start with number 1. If the object distance is 30 cm, focal length is constant. The focal length of the lens required for this practical, this number 1, is a length of focal length 15 cm, so it's constant. So you apply this formula V equal to U F all over U minus F. Substitute U by 30, substitute F by 15 all over 30 minus 15. So 30 times 15 over 30 minus, that gives us 30.0 cm as our image distance. So when the object is 30 cm, the image distance is also 30 cm. So let's record our work. So when U is 30, V is also 30. Record 30.00. Everything to 4 significant figures. So you can see that. So next we go to find U inverse and V inverse. So since U is 30, to find U inverse, I'll now do 1 over 30. I have 0.0333 into 4 places per cm to 4 SF. And also since V is 30, I'll still find 1 over V, that inverse of V, that gives me the same 0.03333 per centimeter. So having obtained our U inverse and V inverse, we go to the table and record the values. So record our U inverse as 0.3 into 4 places to 4 SF, and V inverse at the same 0.333 into 4 places to 4 SF. So having done that, we go to experiment number 2, where we asked to place the object distance at 35. So our U now being 35, when I write 35.00. So go over to the calculation aspect to find our V, that the image distance, where the object distance is 35. So for number 2, when U is 35 cm, focal length is constant 15 cm. We're now looking for the image distance using the formula UF all over U minus F. That is 35 times 15 all over 35 minus 15. And that gives us 26.25 as our image distance when our object distance is 35 cm. Our V is 26.25. So let us record our reading. So for number 2, when U is 35 cm, our V is 26.25. 26.25. So we'll go ahead to calculate our U inverse and V inverse for number 2 experiment. To get our V inverse, since V 26.25, V inverse means 1 over V, that is 1 over 26.25, and that gives us 0.0381 per cm. To get our U inverse, remember that our U is 35 cm. So our U inverse is 1 over 35, and that gives us 0.02857 per centimeter. So let's report our work. So our U inverse for this second row is U inverse is 0.02857 as we obtained 0.02857 to 4 SF. Then our V inverse is 0.0381. So 0.0381, we'll put 0 at the back to make it to 4 SF. Before we continue, there's an error in number 1. It's just going to correct it. So yeah, our U inverse is not 0.33, rather is 0. There's 0 before the 3. 0.0333. Likewise, our V inverse we obtained was 0.0333, the same value. So the error has been corrected. We'll go to number 3. For number 3, the object distance we're working with is 40 cm. That is 40.00. So let's go to the calculation of image distance when U is 40. So we're at it. When U is 40 cm, focal length remains the same 15. There's no change on focal length, please. And then we want to find our image distance, which is UF all over U minus F. Our U is 40, our F is 15. So 40 times 15 all over 40 minus 15. And that will give us 24 cm. So our image distance when the object is 40 cm is 24 cm. So let's report our work. So when U is 40 cm, our V becomes 24 cm. So report 24.00 to 4 SF. We'll now go ahead to find our U inverse and V inverse. So since V is 24 cm, so V inverse should be 1 over 24, and that will become 0.04167 per cm. U being 40, so 1 over U is going to be 1 over 40 is going to be 0.02500 per centimeter. Let's report our work. 1 over V 0.04167. 1 over U 0.02500 per centimeter. So U inverse 1 over U is 0.2025. Report it. 0.02500 at the back to make it to 4 SF. And then 1 over V, we got it as 0.04167. So 0.04167 already to 4 SF. So the next experiment, we'll go to the next experiment where we are now taking our U at 45 cm. So our object distance, that the distance between the ray burst and the lens, taken at 45 cm. We'll go to the calculation to find our V. We'll look at our V. Calculation of V. When U is 45 cm, focal length remains 15, which is constant for the lens. So V is UF all over U minus F. U is 45, F is 15. So 45 times 15 all over 45 minus 15, and that will give us 22.5 cm. So when the object distance is 45 cm, the image distance is 22.5 cm. So let's look at it. So we now report here 22.50 to 4 SF. So we're going to look for inverse of U and inverse of V in the next two columns. So the find inverse of V, 1 over V, that's going to be 1 over 22.5, since V 20.5, and that gives us 0.04444 per centimeter. We also find inverse of U. U is 45 cm. 1 over 45, that gives us 0.044222 per centimeter to report our work. So U inverse is 0.02 into 4 places. And then V inverse is 0.04 into 4 places per centimeter. So that's what we got. We'll now go to the fifth experiment. The fifth is when V is 50. So when U is 50, that when the object distance is 50, let's now go and find the image distance. So when U is 50, focal length being 15 cm, the same formula we'll be applying for others. V equal to UF all over U minus F. 50 times 15 all over 50 minus 15. And that will give us 21.43 cm. So I'm going to record 21.43 cm? No. Because the meter rule, V is obtained for the meter rule. So the meter rule measures to the nearest 1 decimal place. So it can give us 21.43. Rather, we want to record to 1 decimal place, which is 21.4. 21.40 is the nearest answer to 1 decimal place. So our V is 21.40. So we report 21.40 as our V to 4SF. So go on to find our U inverse and V inverse. So our V inverse is 1 over 21.40, and that gives us 0.0467 per cm. Our U inverse, 1 over U, is going to be 1 over 50, since U is 50, and that gives us 0.020 per centimeter. So let's report our work. So our U inverse is 0.02. So we have 0.02 triple 0 to 4SF. Then our V inverse is 0.04673. I have 0.04673 to 3SF. So that is it. So let's go through our readings. So these are the parameters we are asked to measure. The first is the size of the hole on the ray bus, the diameter of the hole. So the ray bus that may contain a crosswire on that hole. So it should be illuminated with light, a bulb inside of it. So the size of the hole we are taking is 2.50 cm. So somebody can take any value, ranging from 1.5 to 4. Don't take the hole is not all that big. So don't take an extra large size. So 1.5 is okay, 2.0 is okay, 3.0, 3.5, 4.0 is okay. So now, what are we measuring? From the experiments, we also find the object distance. That U stands for the distance between the lens and the ray bus, and that's the object distance. That I called it U here doesn't mean that yes, you must see U. You can see Y there, or you can see S. But know that the distance between the ray bus and the lens is what we call the object distance, whether they use U or not. Then V, the distance between the lens and the screen, white screen, we call it the image distance. So you can see a different letter like S, or another letter representing V. It must not be V they will use. Then U raised power minus 1, we have to find that, but that's calculation. After we obtain U, you find the inverse of U. And also V raised power minus 1, So the inverse of V. So from our calculation, when U was obtained was a 30 cm, V remained 30, then our U inverse is 0.03 into 4 places. Our V inverse is same value 0.0333. Then number 2 experiment, when we subjected U, that the distance between the lens and the ray burst out at 5 cm, that's our U. Our image distance we obtained it at 26.25. Our inverse of object, that is 1 over 35, gives us 0.2857. The inverse of 26.25, that is the inverse of image distance, gives us 0.03810. Then when our U was 40 cm, our image distance V was obtained as 24 cm. Then the inverse of U, that is 1 over 40, we have 0.02500. And then the inverse of V, 1 over 24, gave us 0.04167. Going to the fourth experiment, when U is 45 cm, the distance between the ray burst and the lens, 45 cm, that is our U, and V being the distance between the lens and the screen, the image distance is 2.50. The inverse of our U, 45, is 0.02222. And then the inverse of 22.5, that is 1 over V, gives us 0.04444. Then number 5, when U is 50 cm, our image distance V is 21.40. The inverse of our U, 1 over 50, we got it as 0.02000. And then the inverse of V, we got it as 1 over 21.4, we got it as 0.04673. So in all your calculations of on V, please, on V, when you're obtaining your V, you keep your value after calculation to 1 decimal place. Look at it. So 30, 24, 25.5, 21.4. But look at the other one. I wrote 26.25 there because it is possible to estimate 26.25 from a ruler. 26.25 means that the reading lie between 26 and let's say quarter way between 26 and 27. So it's possible to estimate that. Then, having obtained these values, when you want to record your values on the table, you record them to 2 decimal places. So values of V should be minimized to at least 1 decimal place, but on the table, everything should be 2 to 4 SF. Then, to obtain the values of U inverse and V inverse, these ones are obtained by calculation, not by measurement. Keep them to 4 SF. Keep them to 4 SF because they are being calculated. They are not being measured. So after everything, make all the values to 4 SF on the table. So let's go to the graph. And then what are we asked to plot? We have to plot V inverse on the vertical axis against U inverse on the horizontal axis. So the V inverse values are 0.033, 0.03810, 0.04167, 0.04444, 0.04673. And the U inverse values are 0.03333, 0.02857, 0.025, 0.02222, 0.02. When you are plotting, keep your plot to 2 decimal places, at least to 2 decimal places, and be consistent in your plotting. So in our graph, we are plotting V inverse on the vertical axis. So to select our scale, we have to know the least value of V inverse. So the least value there is 0.03333, and the highest value on the vertical axis is 0.04673. So I remember I said in such graph you plot to either 2 decimal places or 2 SF. So let's look at the scale on the vertical axis. So the scale on the vertical axis, so look at the scale, starting from 0, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, and so on. We know that the highest value on the vertical axis is 0.04673. You can see where the plot is, 0.04673. But we have to extend the graph to a higher value because we're going to look for intercept. We have to look for the intercept on the vertical axis. So that will have to increase the value from 0.04, 0.05, 0.06, 0.07. If you look at it, this is 1 over v. If you look at the graph, we reduce the scale. We made it, although the values are not big, but we reduce the scale to 2 cm to 0.01 unit. 2 cm to 0.01 unit. So why did we reduce the scale? Because we're going to look for intercept. So you have to reduce your scales so that you can be able to read the intercept. Because the scale is large. If you are using 4 cm to 0.01 unit, then the graph may not have an intercept. So you have to use a very short scale. Now, let's now look at the horizontal. Horizontal axis is U inverse. And let's look at the readings on the U inverse. Similar readings, 0.0333, and then 0.02857, 0.025, 0.0222, 0.02. We observe that on the vertical axis, the readings were increasing from 0.033 to 0.046. But on the horizontal axis, that U inverse, the values were decreasing. The highest is 0.0333, while the least is 0.02. So the reading ranged from 0.02 to 0.0333. So let's go to the graph and find out how to scale it. From the graph, you can see the scale. We also chose a small scale, where you see the same kind of scale we use on the vertical axis, 0.01 to 1 bus, or 2 cm. 1 bus is 2 cm to 0.01 unit. So 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07 unit. The U bar 1, then per cm, cm per 1. That is the when you write what you are plotting, you must also indicate the unit close to it in a bracket. So it's an error to write what you are plotting without its unit, unless what you are plotting has no unit. So we chose a very short scale for both axes because we are asked to find the intercept. So then after plotting the graph from our readings, we obtain an inverse shape graph. You can see the graph. And doing a very good estimation, we'll see that, or manipulation, you see that all the points are in a straight line except one. You can see, and that one that is not in the straight line had to be very close to the straight line, showing a perfect experiment. So having done that, we'll go to the next question. The next question is, we should find the slope of the graph. To find the slope of the graph, you choose any two coordinate points. Mainly choose the points that are on the straight line. But if the points on the straight line are very close to each other, then take one on the straight line and take another that may not be on the straight line. But if they are far from each other, then take the two of them from the straight line. That'll be better for you. So we chose this point on the straight line, which is 0.4673. Or 47 approximately, since we are plotting to two decimal places. So 0.047, and then the value, the lower coordinate on the vertical axis, 0.02. then 0.02. So the coordinates on the vertical axis are 0. Well, we are taking our slope 0.47 approximately. Then the lower coordinate is 0.02. If you come down on the horizontal axis, we have about 0.4. We're going to read letter 0.04 something. Then on this other one, we have 0.02. The lower coordinate on the horizontal axis is 0.02, while the higher coordinate is around 0.0. Make it clear. 0.04. We'll get it as when we do the sloping. So that's where we are taking our values. So let's look at the slope. So to find the slope, we'll take the formula, change on v minus 1 axis, that the vertical axis, all over change on u minus 1 axis. So the vertical axis, the upper coordinate is 0.47 approximately. The lower coordinate is 0.02. So that one will have the 0.047 minus 0.02 on top. Then on the horizontal axis or the abscissor, then they look at the change. The upper coordinate there, if you go down, is also the same 0.047. If you trace it and read very well. And then the lower coordinate is 0.02, the same coordinates on both axes. So we see how by under 0.047 minus 0.02. So when we subtract, we have slope equal to 0.027 all over 0.027, and that slope is nothing but 1.0. The slope of the graph is 1.0. The next we're asked to find the intercept on both axes, C1, the intercept on vertical axis, and then C2, the intercept on the horizontal axis. If we read the intercept on the vertical axis, you have 0.06. Each line is 0.01. So 0.001. So 0.06, 0.061, 0.062, 0.063, 0.064, 0.065, and 0.067. That's the intercept on the vertical axis. Then we'll go to the horizontal axis. The intercept on the horizontal axis, we read it. We're going to see how 0.061, 62, 63, 64, 65, 66, and also approximately 0.067. So the intercept on both axes are equal for this kind of experiment. So having done that, we have our C1 as 0.0670 per cm. That the intercept on vertical axis. Then the intercept on horizontal axis is the same 0.0670 per cm. And we asked in number SI to find the mean value of the intercept, that is the average. So that is C. So C is C1 plus C2 over 2. We add the two values and divide by 2. And of course, we get the same value C, which is equal to 0.0670 per cm. Then the next question, we have to evaluate K. K equal to 1 over C. That's one over the mean intercept. That's going to be 1 over 0.0670, and that will give us 14.9, approximately 15.0 cm. So what does this scale represent? This scale represents the focal length of the lens given to you in this experiment. And the focal length to be provided for you is a length of focal length 15 centimeter. So if you have an accurate experiment, your value should be very close to 15 cm. If you're far from it, then you do not do a good experiment. The next thing is precautions for this kind of experiment. Precautions should include that I avoided error due to parallels in measuring or in reading the meter rule, because you use the meter rule to measure your U and your V in the actual experiment. So I avoided error due to parallels in reading the meter rule, and also I made sure that the source of light was steady. Or that the ray bursts were illuminated with a bright source of light. So these are some of the precautions that you should note here. Then you should also know how to solve problems that involve converging lens, how to manipulate problems on converging lens, how to draw the ray diagrams, especially when the object is placed between the principal focus of a converging lens and the optical center, and what is meant by the principal focus of a converging lens. So you have to know the definitions to help yourself. So stay connected. We shall be bringing to you the model 3 part of this experiment, and also the experiment on electricity and other aspects. The whole thread in this alternative B will be given to you in this video. So stay connected. Subscribe to the channel if you are not subscribed. The video is playing. Look beneath the video. Under the video, you see the channel's name, Best Science Brain, and the subscription icon or button. Tap on it only once and get subscribed and get connected and follow others to learn and pass the examination. Thank you.